Yeah. Yeah. Last class we discussed about this bar problems. So how to identify the deflection for a bar. There's another type of problem where you have some deflection or some deflection is given. So based on that, you have to identify what is your stress and other things. Okay. So we will try to solve this one. So you can able to see that in the figure, there are two forces which is acting at the center of your bar. And they mentioned what is the length, right? So the length is AC is around, so let me name this. So you have A, so B, C, D, and E. So these are the locations. So they mentioned that from A to C, so it is 500 mm. So which means AB. So this length will be around 250 mm. So this is also 250 mm. And they mentioned what is the cross section area. It is around 8 centimeters square. So we have to convert it to mm, right? So because everything is in mm, right? So next CE, from C to E, it is 750, right? They mentioned it is 750. In that case, 375. So this will be 375 and this will be 375. Okay. So these are the lengths which is mentioned here. So we split it and the area for this is 4 centimeters square. That is also mentioned. So what you have to do is you have to identify what is the stress developed, right? And they mentioned that there is a block which is at the distance of 0.1 mm. So after 0.1 mm, what happens? There is no deflection. Okay, so there is a restriction in the deflection. So we have to identify this as based on this, right? So that is what the distance here. So which is mentioned. The total length of the bar is 1250. Okay, this is what the data. First, we will convert what are our units. Then we will proceed accordingly. First, we will deal with what is the area. So our area A1 is 8 centimeters square, which means 8, right? So 800, right? So 800 mm square. So 1 centimeter is 10 mm. So I am multiplying. So 100. So similarly, A2. So area on this location will be, it is 4 centimeters square, which is 400. So it is 400 mm square. Now let us proceed with the usual procedure. The first thing is I have to split this into elements. So how many elements you have here? Can anyone?
So 4 elements, sir.
Yeah, so we can split this into 4 element, right? Correct. Very good. So this is element number 1, which is linking nodal point 1 and 2. Then element number 2, element number 3, and element number 4. So 3, 4, and 5. So these are my elements. So element 1, element 2, element 3, and element 4. So 4 elements. So in this 2 element is for this location, and the other 2, this one is for this location, for this particular bar. Okay, so this is the splitting. So we split it. Okay, so and everything is having a displacement u1, u2, u3 accordingly. So this is u1, your u2, here your u3, here your u4, and here your u5, right? Which is for the force F1, F2, F3, F4, and F5, right? So now we will identify what are the elements. So what is the stiffness matrix for each element separately. So we'll proceed one by one. So let me consider the elements different. Element 1. Let me start with element 1. If I consider element 1, so this is my element. So this is my element which is connecting nodal point 1 and 2. So if I consider what is the length, right? So the length of this element L is 250 mm. So I'll call L is equal to 250 mm. And you know what is the area for this? So area is, so it is 800 mm square, right? For this element, it is 800 mm square. Okay. So Young's modulus is also same. It is 2 into 10 power 5 Newton per mm square. So it is 200 gigapascal. I'm converting in Newton mm square. So I'll get 200 is 2 into 10 power 5 Newton per mm square. Now you know what is the formula for this. So element stiffness matrix K12. It is A E by L 1 minus 1 minus 1 and 1. Let us solve. So A is 800, E is 2 into 10 power 5, L is 250, and you have 1 minus 1 and 1. So what is the answer for this? 800 into 2 divided by 250. What is a K12? Okay, you are getting 6.4 into 10 power 5. Okay, so let me consider 1 into 10 power 5 as an outside term. Remaining, I will put it in. So which means, so you'll get 6.4 minus 6.4 minus 6.4 and 6.4. So this is for element 1. So next we proceed with element 2. So we proceed with element 2. So K23. So connecting nodal point 2 and 3. Look at this particular thing. So we are splitting at the middle. So your area is same, which is 800. Your length is also same, which is 250. There is no change in the stiffness matrix. Okay, so since there is no change, I can consider this same stiffness matrix. So whatever we consider here, right? So no change. So I will have it directly. So element 2 is also over. So when I go for element 3, so it is K connecting nodal point 3 and 4. You know, it is A E by L 1 minus 1 minus 1 1. So for element 3, so this is my nodal points, so which is connecting nodal point 3 and 4. So your area is 400 mm square and your length is 375 mm. So there is a difference in your area and your length. So you can able to see that it is 375 and it is 400 mm square. Young small is the same. So in that case, so what you will get area as 400 into young small is 2 into 10 power 5 divided by 375. So this is what you will get the value. So again, so you'll get plus 1, minus 1, minus 1 and 1. Okay. So what will be the value here? So you are getting 2.13. Okay, good. Thank you. So it is 2.13 minus 2.13. So minus 2.13 and 2.13. So this is my value. Right. So your element 3 is also over now. We'll go for element 4. I think there is no difference in element 4. So same as element 3. 4, 4, 5. Right. Will be equal to same thing. Okay. So this is my next element. So I got element stiffness matrix for all these elements. So element 1, element 2, element 3, and element 4. So everything is over. So the next step, what I have to do is I'm going to identify what is the size of my global stiffness matrix. Size of global stiffness matrix. Right? How to identify the size? It is number of nodes into degrees of freedom per node. So this is what I am going to do. So number of node, just look at this. So your number of nodes is 1, 2, 3, 4, and 5. So number of node is 5. And each node is having 1 degrees of freedom. So 5 into 1, which is 5. So 5 cross 5 will be my size of my global stiffness matrix. Okay. So now let me write out. So what is my K matrix? Okay. So K, capital K, denoting 1, 2, 3, 4, 5. Sometimes it is difficult so to write all these numbers. So you can write directly as capital K. That is enough. So it is not compulsory you have to write this. Okay. Just for reference. Right. So this is equal to 1 into 5 is a common term. I am taking that out. So remaining, so you will have a matrix like this. Okay, it's a 5 cross 5 matrix. Right. So the numbering for this will be like this. So we have 1, 2, 3, 4, and 5. Similarly, 1, 2, 3, 4, and 5. So you can able to see. So there are values. There are 5 columns and 5 rows. You can consider this as a tabulation also. It is up to you. So now let us address this, right? So one by one. So for element 1, you can able to see that you have nodal point 1 and 2 connected. So when I address, it will be 1, 2, 1, 2. So this is my address. When I go for element 2, it is connecting 2 and 3. So my address will be 2, 3, 2, 3. And I can go for element 3. My address is 3, 4, 3, 4. And last element will be addressing 4, 5 and 4, 5. So this is my address. So let us assemble this accordingly. So in this matrix, the first one is 6.4. So it is first point is 6.4, which is connecting nodal point 1 and 2, right? So let me address it. I'll be write it here. So what will get? I'll get 6.4 here minus 6.4. So minus 6.4 and 6.4, right? So sometimes if you have a larger number of matrices, right? So you know that there is a one property in stiffness. So stiffness matrix is always symmetrical matrix, right? So in that case, you can concentrate on upper triangle. No need to concentrate on lower triangle. Okay, later you can substitute it accordingly. You know that Aij is equal to Aji, right? You can substitute it accordingly. So that you concentrate only on the upper triangle. Other things you can just put symmetric. Okay. From next elements, I will consider only the upper triangle. So the other triangles out, this term is symmetric. Okay. So first element is over. The second one, we are concentrating on 2, 3. So 6.4 minus 6.4 minus 6.4, 6.4. So what will get? I will get here 2, 3. So 2, 3. So plus 6.4 minus 6.4. So 3, 3 is here, which is 6.4. This one I am not going to fill because it is upper triangle. I will put X. X indicates its symmetry. Okay. So this is also X. So these are all X. Okay. So later you have to write it accordingly after you recognize it. Right. Okay. This part is over. Next, we will go for element 3. So when you go for element 3, so you can see that element 3 is connecting 3 and 4. So where is my 3? 3 is here. So 3 cross 3. So what is the value? It is 2.13, right? So plus 2.13 minus 2.13. So this is X because I will substitute it, and this is 2.13. Okay, 4, 4. Next, 4, 5. So 4, 5 is again 2.13. So 4, 4, 4, 5. So 4, 4 is 2.13 plus 2.13. 4, 5 is minus 2.13, and this is 2.13. Okay, so these terms are symmetric. No need to write. Okay, so only when you're substituting, then you concentrate on it. Right, other things you can just leave it. So the other part is whatever which is not filled, you consider that as 0. So this is 0, this is 0, 0, 0, 0, and 0. So this is my stiffness matrix. Now what I can do, I can write it as F is equal to K into U. I'm going to directly write the F value because F is only on the point nodes. So it is in nodal point 2. This is at nodal point 2. And this point, so it is an opposite direction, right? So what is the nodal point? So 1, 2, 3, 4. This is nodal point 4. Okay. So your force is acting only on nodal point 2, 1, 4. And if I consider right hand side is positive, the other one has to be negative value, right? So you can able to see one is in the other direction. So when you write it accordingly. Okay, so 30 kilonewton and 20 kilonewton. So I will write it directly. So what I going to do is let me consider. So your F is equal to K into U. Right? Let me write it out. So what is your F? F will be 5 cross 1 matrix. So indicating five nodal points. So nodal point 1, no force. Only at nodal point 2, you are having 30 into 10 power 3. So this is 0. This is 30 into 10 power 3. This is 0. This is minus 20 into 10 power 3. And this is 0. 1, 2, 3, 4, 5. So this is my F term. Force. So now 1 into 10 power 5. Your stiffness matrix. Stiffness. So this part. So this part is symmetric. Right? You can write as symmetric. That's enough. So into your values of your U1, U2, U3, U4. So U1, U2, U3, U4, and U5 as my values. Right? So I have mentioned what is my data. So all the data. So I have assembled, everything is ready. Only thing is I have to apply my boundary conditions. What is my boundary condition? Just look at the problem. So the first condition is nodal point 1 is fixed. So if it is fixed, there is no displacement. So your U is 0 at nodal point 1. So which means U1 is 0. Other things are free. You have displacement. At the last, you think about it. So nodal point 5. So it can displace only up to 0.1 mm. Right? So then U5, they given the value, which is 0.1. So that is what we are going to substitute. Okay. So in this case, only 1 is 0, which is 0. So only U1 is 0. U2, U3, U4, we have to identify. U5 is 0.1. Right? Now you can't strike this first row, first column. That is not possible for U5. Only possibility is for U1. U1 is 0. Since that is 0, I can strike the first row and first column. Right? Remaining terms you have all the values. Okay. So what are the remaining values? Let me write it again. Now I'm going to expand it, but there is no other way because we are going to multiply it. So you will get confused. So on writing, I'm not going. I am going to fill up my symmetric. What are the data? First, let us fill up the upper triangle. So you are getting this value, right? So these are my values, right? Into U2, U3, U4, 0.1. U5 is 0.1. These are my values. Now let me fill it up because I need to write it in an equation, right? So this will be here. So this will be minus 6.4, 0, 0. So what is this? Minus 2.13. And this will be also be 0. This is minus 2.3. Right? Symmetric. Right? Aij is equal to Aji. I am filling it out because I'm going to multiply. Now I will get 4 equations, right? Relating it. So I am not striking this, right? Because when you are multiplying, you will get that value. So based on that, you will identify. Okay. So multiplying it, while multiplying it, so this one, so the last equation, I think I can't able to use, right? It is just a value which will be multiplied on other values. So that is why it is useful. Whereas the last equation, it won't, right? I think so, right? Let us solve it. So it is 30 into 10 power 3 is equal to 1 into 10 power 5 into multiplication of this 12.8 U2. So we are getting 12.8 U2. Then minus 6.4 U3 minus 6.4 U3. And I think 0 into U4, 0 into 0.1. So everything becomes 0. So this is my first term, right? So when I simplify, so I will get like 12.8 U2 minus 6.4 U3 is equal to 0.3. equation number 1. Next, let me go for the second equation. 0 is equal to minus 6.4 u2. So 1 into 10 power 5 is common. Let I'll write it out. Minus 6.4 u2 plus 8.53 u3 plus 8.53 u3 minus 2.13 u4 minus 2.13 u4 is equal to 0. So that one, so 0 into 0.1, that is 0. So we are going to consider. So leave it. So this is my term, right? So this is my second term. So we are having it. So which means I can write as minus 6.4 u2 plus 8.53 u3 minus 2.13 u4 is equal to 0. This is my equation number 2. Okay. Next, we'll proceed with the next equation, equation number 3. So minus 20 into 10 power 3 is equal to 1 into 10 power 5 into third equation 0 into u2 0. So this one minus 2.15 into u3. So minus 2.13 into u3. 4.26 into u4 plus 4.26 into u4 and minus 2.13 into 0.1. So minus 2.13 into 0.1. So this is my value, right? So what we'll get? So let me equate it. So minus 2.13 u3 plus 4.26 u4 is equal to, so this is 0.213. So this is 0.2, right? So minus 0.2 plus 0.213, right? This is what I will get. So when you bring it on the other side and dividing, you'll be getting like this. So I'll get this is minus 1.23 u3 plus 4.26 u4 is equal to, what is the remaining value? So subtracting it, you'll get 0.013, right? This is equation number 3. Okay, don't use the last equation. Okay, so don't use the last equation, even though you can get it as an equation. I think even though if you apply it, so you have only one term, which is u4, right? So you will say that u4 is equal to 0. That is not possible. Okay, this equation actually I have to cancel this. So first one, first column. So whenever you have the value of displacement, it has to be cancelled. But since this value I am using it, I am not cancelling. That's it. Okay, so don't use the last one, last column. When you do that, what you'll get? You'll get 0 is equal to minus 2.13 u4 plus 2.13 into 0.1. You'll get something, and you'll get what is your u4. Right? I don't know whether this will satisfy the other answers. Right? So don't use that. So only first 3 equations. So whatever you don't know the unknown, right? So we don't know the values of these 3. So with respect to that, whatever the matrix you are getting, that alone you concentrate. Others you don't need to concentrate. Okay. So now you solve this 1, 2, and 3 and find out what is the values of u2, u3, and u4. So now can you tell me what is the value for this? Right, so solving this 3. What's the value you are getting? Have you tried?
Sir, 0.04 means answer.
Which one? First one.
Yes, sir. U2.
Okay, 0.0417.
17.
Okay, thank you. Second one, U3.
0.036.
0.036 mm. U4.
0.021.
0.02 mm. Right? Okay, very good. So we got all these values, right? So only thing is I have to go for proceeding with what is the stress value. So they're asking, the main problem is to identify what is the stress, right? Stress in each element. Okay, so we have the elements accordingly. So nodal point 1, 2, 3, 4, and 5. And this one is 0. You don't have displacement here. And if I consider here U2, which is what we identified, which is 0.0415, and U3 is 0.036, U4 is 0.02, and this is 0.1, which is already identified, right? Which is already given. Okay, and you know what is the displacements. So this is 250, 250, 375, and 375. Okay, so only thing is I have to identify the stress. So stress in each element. So for element 1, element 2, element 3, and element 4. So let me go one by one. So for element 1, it is Young's modulus, which is 2 into 10 power 5, into subtraction of this. So element 1 is carrying nodal point 2 and 1. So subtraction of 2 minus 1. So which is 0.0417 minus 0 divided by length. So length is 250. So change in length by original length, which is giving you strain. So what is the value you are getting? So the value here is 33.36 Newton per ounce square. Right? A positive value, it's tensile. Okay. So let me go for the second one. So stress for element 2. Element 2 is connecting 3 and 2. Right? So these are the nodal points. So 2 into 10 power 5. So 3 is 0.036 minus 0.0413. So final minus initial, right? So divided by 250. Right? So what you will getting? Minus 4.56 Newton per ounce square. So since it's a negative, it's a compressive type of loading. Stress in third element, 2 into 10 power 5, same procedure. So U4 minus U3. So 0.02 minus 0.036 divided by length. Length is 375 now. 375 minus 8.53. Are you getting this? Check it out.
Yes, sir.
Yeah. The last one. So stress in element 4, which will be equal to, so again 2 into 10 power 5. So it is connecting 5 and 4. So 0.1 minus 0.02, right? Divided by 375. You're getting 42.667 Newton per ounce square. Tensile load. Okay. So positive value. Yes. Are you getting this value?
Yes, sir.
Yeah. Now,